So today's lesson is an in-between lesson. We're going to look at some more indeterminate forms of L'Hopital's rule. So there's not a new homework assignment. The day 8 homework assignment is just due next class. So you basically had 2 nights to work on that assignment. So we already learned on day 8 about the indeterminate forms of 0 over 0 and infinity over infinity, and how we can do L'Hopital's rule for them. Take the derivative of the numerator, derivative of the denominator, reevaluate the limit. So today we're going to look at several additional indeterminate forms, and in your notes packets, you're in the day 8.5 one. So the three are, you could have an indeterminate product. So that's whenever you have 0 times some type of infinity. So this could be a plus infinity or a minus infinity that we're multiplying by. Okay, but just note it's still a times there. So it could be times either positive infinity or negative infinity. If you have an infinity minus an infinity, that's an indeterminate difference. And we have 3 exponential indeterminate forms that we'll talk about as well. So we'll start off with our indeterminate product. So if you have 0 times infinity or 0 times negative infinity, what we want to do is we want to rewrite it as a quotient. So dividing by something is the same as multiplying by its reciprocal. Well, the same is true. If we're multiplying by something, it's the same as dividing by its reciprocal. So if you have a 0 times an infinity, you could take the infinity thing and make it a 1 over in the denominator, or take the 0 thing and make it a 1 over. It might not always be obvious what we should do for this, but you basically just pick one you think would be best. If you get stuck, try the other one. So first off, we're going x approaches 0 from the right. It's got to be 0 from the right and not just 0 because of our natural log function. So this is our graph of natural log. So x, as we approach 0 from the right, is just 0. Natural log, when we approach 0 from the right, is negative infinity. So that's our indeterminate product of a 0 times one of our infinities. So we want to rewrite this as a quotient. And we have 2 options for what we could do. We could move the natural log and make it 1 over natural log in the denominator. Or we could move the x and make it 1 over x in the denominator. And basically what we want to do is eventually get to something that we can evaluate. We could try both of these, but hopefully one of them will neaten up a little bit better. Well, the first one there, the one with the 1 over natural log of x, that's really natural log of x raised to the negative 1. So if you were to eventually do its derivative, you would get a chain rule and you'd keep getting natural log x's. But in the right-hand one, the natural log of x in the numerator, its derivative is 1 over x. So then we'll have something that no longer has natural logs, which are sometimes messy to work with. So we're going to work with this one here to start, and we'll see if it works out. So we already knew natural log of x as you approach 0 from the right is just negative infinity. For 1 over x, if you have tiny positive numbers in the denominator, think of it as like 1 over 1,000. When you do a keep change flip for that, they'll end up being big positives. So this will really be positive infinity in the denominator. So notice that leads us to a L'Hopital's case. That's the whole reason that our technique is to write it as a quotient. So we'll do L'Hopital's now. So we'll have limit as x approaches 0 from the right. Natural log is 1 over x. Think of this as x to the negative 1. So its derivative would be negative 1 x to the negative 2, or in other words, negative 1 over x squared. Off to the side, I'm going to neaten that up. So if I do a keep change flip, one set of x's will wipe out and we'll have a negative. So this will really just neaten up to negative x. Note that was not a L'Hopital's I did there. I was just neatening up. And you'll often want to neaten up after you do your L'Hopital's to see if it's something you can evaluate. Well, now let's reevaluate. As x goes to 0 from the right, negative x is just going to approach 0. So basically what that's telling us about our product is in that product of 0 times negative infinity, we must have been heading to the 0 quicker than the natural log was heading to the negative infinity. So the 0 basically took control of that product. So next up, let's look at our infinity minus infinity indeterminate form case. And let's just show you why this is considered indeterminate. So most people would say if you have infinity minus infinity, oh, that's just 0. Well, let's go with that assumption. Infinity minus infinity is 0. Well, let's add 1 to both sides, and we'll get this row. By the associative property on the left, you can do any of those additions and subtractions in either order. So let's do the infinity plus 1, and that's what we're showing here. Well, infinity plus 1, that's just an infinity. So now we have infinity minus infinity. And that's equaling 1 now by our simplification. But we said infinity minus infinity is 0. So we got a contradiction there, so something's not quite right about assuming infinity minus infinity is 0. If that doesn't convince you, let's do another one. Let's say we added infinity to both sides. Well, then group your two positive infinities together here. Well, infinity plus an infinity should just be another infinity. Well, now we have infinity minus infinity equals infinity. But we said infinity minus infinity is 0. So how are we getting that? And then if you're still not convinced, one last option. So let's replace infinity with infinity plus infinity. Because we said a second ago, okay, if a huge number plus a huge number, it's still just a huge number. Well, then regroup it. And if we're saying infinity minus infinity is 0, then that's saying that infinity is equal to 0. So the whole purpose of these three things is, if you're saying, oh yeah, infinity minus infinity is 0, we can use just algebraic properties that we have and properties of numbers that we have to show that we're getting some inconsistencies there. So the whole purpose of these three things is just to convince you, okay, maybe we can't just say infinity minus infinity is 0. Maybe it's something that's indeterminate, meaning something we have to think about a little more. So our case, if we switch to the next one, for infinity minus infinity, the technique is if you have that to get a common denominator. And once you have that common denominator, bring it all together as a single fraction, and then it's usually a L'Hopital's case. Well, for this one here, in both those, the denominator is going to get really tiny. And if you do 1 divided by a tiny thing and do a keep change flip, that's going to end up huge. So this is going to be infinity minus infinity. Now you might be saying, well, what about if we go 0 from the left? Well, 0 from the left would make the 1 over x be negative infinity. And then we'd have minus 1 over sine x, 0 from the left would be negative infinity. That would be a plus. Notice that's still really infinity minus infinity. So either side of 0, we will get an infinity minus an infinity. So we want to get a common denominator. So let's multiply this by sine x and this by x. And this will eventually lead us to sine x minus x over x sine x. Well, let's try and evaluate this. Sine x is 0, x is 0, so we get 0 in the numerator. We'll have 0 times 0 in the denominator. Notice we have 0 over 0. Okay, great. That's a L'Hopital's case. We can handle that. Derivative of sine is just cos. Negative x will be negative 1. In the denominator, we have to do a product rule. So derivative of x is 1 times regular sine x plus regular x times derivative of sine, which is cos x. If we sub in 0 into the x in cos, that's 1. 1 minus 1 is 0. Derivative of sine, or sorry, not derivative, subbing in 0 for x in the sine is 0. And then we'll have 0 plus 0 on the bottom, so that again is 0 over 0. Okay, we got to do L'Hopital's again. Derivative of cos will be negative sine. Derivative of negative 1 is 0. On the bottom, derivative of sine x is cos x. And then we got to do a product rule for that second term. So we'll have 1 times cos x plus x times negative sine x. And we'll reevaluate. Sine of 0 is 0, so we get 0 on top. On bottom, cos of 0 is 1, plus cos of 0 again for that next one is 1. And then 0 times 0 for the third one. So we get 0 over 2, which is just 0. So in this case, infinity minus infinity happen to approach 0. Not always going to be that. And let's think about why it makes sense that it did end up this way. 1 over x and 1 over sine x, they both, or sorry, not 1 over x, 1 over sine, x and sine x, they both approach 0 at similar rates. And we know that from our limit as x approaches 0 of sine x over x is equal to 1. So we know that when x gets close to 0, sine x and x will get small at about the same rate. So therefore, these infinities are essentially about the same bigness, you can think of it as, and that's why it's approaching 0 in this case. Will not always be that. All right, we're going to skip the next slide and go over to case 3. So we have 3 indeterminate forms for exponentials. So first off, notice in that blue box, we have 0 to the infinity is not indeterminate. And the reason for that, if you have something getting close to 0, think of it as like 1 over 100, and raise it to a huge number, so let's say to 1,000, that's just going to make it super, super small every single time, so it's going to approach 0. So that's not indeterminate. If we have 0 to the 0, it all depends on which one goes quicker. So the number that's written in here is implying that that's the one that goes quicker. If the base is getting small, quicker than the exponent's getting small, then we'll approach 0. And remember, when you're raising to a tiny exponent, think of it as you're taking a big root of it. And if you had like 1/2 and took like the 100th root, that's going to actually send it close towards 1. So decimal values with big roots makes it grow towards 1. And that's where it's going to come into play in this next one. If the exponent is heading towards 0 quicker, so that's going to have the power, and that's going to send our term towards the value of 1. Next one, infinity to the 0. So if the infinity goes quicker, that basically means our base is getting bigger, faster than our root is growing. Because remember, 0 in the exponent is like you're really having a big root, like a 100th root, a 1,000,000th root. So if that base is growing bigger, it's going to end up blowing up and go to infinity. But if we keep taking a bigger and bigger root, because again, tiny exponent means you're just taking a bigger root, that should head towards 1 then. And the last one, 1 to the infinity. If it heads towards 1 quicker, then it'll just approach 1, because 1 raised to anything is 1. But if it's going to the infinity quicker, it depends on which side of 1 we are approaching. If you're a little bit below 1, and the exponent has the power, then that's going to send it smaller, smaller, smaller towards 0. So this would be if 1 from the left. But if you're on the right side of 1, so a little bit bigger, but the exponent has the power, that's going to make it blow up. So that would be 1 from the right. So that's just to kind of walk you through why those are indeterminate. You won't have to know that on a problem. You'll just have to know that these three are indeterminate exponential forms. So if we go down to the bottom, as x gets huge, a over x is going to get small, meaning that inside's just going to be 1. And as x gets huge, b to the x is going to get huge. So that's going to be a 1 to the infinity. So that's our third case up on top there in our table. So this is an indeterminate form. So the technique for this is just an aside. If I had e to the natural log of 7, I want you to think about what that equals. Hopefully you know that that equals 7. So our technique that we're going to do is we're going to switch these as e to the natural log of whatever our stuff is. And that's what this is saying here. Take your exponential thing and rewrite it as e to the natural log of stuff. So in this case, we're going to do limit as x approaches infinity. And we're going to do e raised to the natural log of our stuff. And the reason we can do that is basically demonstrated over in that e to the natural log of 7 equals 7. The left side was still equaling 7. It just looks a little different. So we haven't actually changed the value of it at all. Well, what we're going to do is we're going to just work with the exponent. And know whatever the exponent is approaching, our answer is just e raised to that. So we're going to now work with just the limit of the exponent, because that's where all the x's are. But at the end, whatever we get for this limit, our answer will actually be e raised to it. So if we get that this limit is 14, then our answer is actually e to the 14. So what I like to do with these is I like to go down a little bit, and I like to write at the end e raised to, and that's just a reminder for me at the end, oh, don't forget to put it back with an e, because it's easy to forget that. Well, by law, the whole reason of doing this with a natural log is so we can use log laws. We can swing that b to the x out front. Well, b times, sorry, this was an infinity, not a 0. B times an enormous number is an enormous number. As x gets huge, a over x goes to 0, and natural log of 1 approaches 0, so we've got a 0 times an infinity. Well, that was case 1 that we saw, where we want to rewrite this as a quotient. We saw it's easier to leave the natural log b, so let's bring the x down as a 1 over x. I'm going to leave the b where it is with the natural log. And we'll now have 1 over x on the bottom. The natural log is still approaching 0, but 1 over x now, if you have 1 over enormous numbers, that approaches 0. And this is now something we can do with a L'Hopital's case. So natural log's derivative is derivative of the inside over the inside, and we got that b out front that we'll just leave. So derivative of 1 is 0, that's gone. This a to the x, think of it as a times x to the negative 1. So we're going to have negative a times x to the negative 2, or in other words, negative a over x squared for our derivative, over the original inside, which was 1 plus a over x. And that b, again, was just because that was the coefficient. So that just gets thrown in the numerator. Over our derivative of 1 over x, well, that's like x to the negative 1. So we'd have negative 1x to the negative 2, or in other words, negative 1 over x squared. Well, let's neaten this up a little. I'm going to maybe write it off to the side. Right now we have negative ab over x squared over 1 plus a over x. Dividing by negative 1 over x squared is the same as multiplying by x squared over negative 1. So these x squareds will wipe out, and we can take care of the negative wherever we want. I'm going to wipe it out with that negative there. So we're just left with the limit as x approaches infinity of ab over 1 plus a over x. As x goes to infinity, the a over x is going to 0, so this will just be ab over 1, or in other words, ab. But don't forget, that's really just our exponent, so our actual answer is that this original limit should approach e to the ab. All right, going over to the next page. This one's pretty easy to see what we have. It's going to be a 0 to the 0, which is one of our indeterminate forms for exponentials. So our technique, we're going to do e to the ln. So x approaches 0 from the right of e to the natural log of x raised to the x. And then we're going to do the limit of just our exponent. And I'm going to write off to the side to remember to do e raised to something for our answer. We'll swing our x out front again using our log laws. Now this is actually the first one we looked at in case 1, so we could just take our answer from that. But just for the practice, just real quick, this should be 0 times negative infinity. That's indeterminate form, so we need to bring one of them to the denominator. We saw that we wanted to bring the x to the denominator, so that was 1 over x. That one's still negative infinity, and 1 divided by a tiny number when we do a keep change flip would give us a big number. This then gives us our L'Hopital's. We'll have 1 over x over negative 1 over x squared when we do the derivatives. We saw in that case 1 example when we did our keep change flip, we ended up with negative x, and this just gave us 0. But we still got to do e raised to, so our answer is really e raised to the 0, or in other words, 1. So don't forget at the end, again, to do the e raised to, because we're just finding the limit of the exponent. We're going to skip the next slide, and we'll finish off with this last example. Oops, I wrote skip on the wrong one. All right, x when it goes to infinity gets huge. Denominator when it goes to infinity it gets huge. This is a L'Hopital's case. Derivative of x is just 1. Denominator will have to do a chain rule, so we'll have 1/2 x squared plus 1 raised to the negative 1/2, and then times the derivative of the inside, which is 2x. And then let's neaten this up. The negative exponent can switch to the numerator. So we'll have square root of x squared plus 1 in the numerator now, and then 2x times 1/2 is just x. So if we evaluate again, we're going to get huge over huge. Let's do L'Hopital's again. So this will be 1/2 x squared plus 1 to the negative 1/2 times 2x all over 1. Bring the negative exponent down. we're going to have square root of x squared plus 1. In the denominator, 2x times a half gives us x. Well, hopefully that looks a little familiar. That's right where we started. So if it's cyclic like that with L'Hopital's, this just tells us we can't use L'Hopital's. So we've got to do this algebraically. Luckily, its x approaches infinity. So that basically told us our horizontal asymptotes. When you go to the infinities, you want to think the biggest powers. So this limit will be equal to the limit as x approaches infinity of x over, we can think of it as square root of x squared. Square root of x squared is really absolute value of x. We can resolve the absolute value by the fact that we're going to positive infinity. So our inside would be a positive, so that is just whatever it is. So this becomes x over x, and that's just going to end up being 1. So if by chance you ever got a cyclic case, you would have to do it by some other methods. I think pretty much all the ones, the L'Hopital ones we see, will be ones that you can resolve with L'Hopital's rule. That's it for this video on our additional indeterminate form cases. Again, you just have the day 8 homework to be doing. There's not a new assignment for day 8.5. Have a great rest of your day.